In this video, I'm talking about conditional probabilities and Bayes formula. We start with a simple example and then I describe how Bayes formula is applicable to diagnosis testing, and we finish this video by example on the diagnosis testing. Okay. Just first, let's start with a simple example. There is no conditional probability on this example, but it makes a basis for our next example that will have a conditional probability. Okay, in this problem, we have two boxes. We call them left box and right box. In the left, we have 3 black marble and 7 white marble. On the right, we have 5 black marble and 5 white marbles. If I ask you, a marble is picked from one of the two boxes, what's the probability of this marble being white? What would be the answer? Okay, as long as the probability of choosing a marble from any of the boxes are the same, we can add up all the white marbles, 7 and 5, and divide that to total number of marbles. So the probability of picking a white marble, given that likelihood of picking any boxes are the same, would be 0.6. Okay, now, next question. If I tell you that we have a sneak peek and we find out that the marble has been chosen from the left box, so what would be the probability of the same question? Like, what's the probability of a white marble being picked? In this case, knowing that the marble is coming from the left box, the probability is 7 divided by 10. So that's the probability conditioned on the left box is being used to pick the marble. If we ask the same question, but this time we know that the marble has been chosen from right box, what is the probability this time? So that's how we write it. Probability of a white marble given the right box is chosen is 5 divided by total number of marbles, 0.5. So that's the meaning of a conditional probability. Okay, what's the formula? What's the Bayes formula for conditional probability? Based on the Bayes theorem, probability of A given B is equal probability A and B happening, or intersection of A and B, divided by probability of B. Or we can write that in a different form. Probability of A and B happening is probability of B multiplied by probability of A given B. Also, symmetrically, we can write it based on the probability of A. Probability of A and B happening is probability of A multiplied by probability of B given A. So these two are equal. So let's ask a different question. Or actually, it's not a different question, it's the same as question 1. This time we are using the Bayes formula to solve it, right? So we're saying that what's the probability of a white marble is chosen? Okay, probability of a white is partitioned into two conditions. It can be a white coming out of the left box, right? Pick left box and pick white, plus probability of pick the right box and pick white. So probability of left box and a white is probability of left box multiplied by probability of a white given the left box, plus probability of right box being picked and probability of a white being picked given that we are dealing with the right box. So knowing that the probability of picking any box is similar, is the same, that means that probability of picking left box or right box is 0.5. Okay, so we put 0.5. Probability of the white coming from the left box is 7 white divided by total number of marbles, 10, plus probability of right box being picked, which is again 0.5 because it's the same probability of as left box, multiplied by probability of a white coming out of the right box, which is 5 divided by total number of marbles in the right box, 0.5. If we do this calculation, we end up with the same number, 0.6, that we found previously without using conditional probabilities. So this is an example to show how the conditional probability is used to solve problems. Okay. In the previous slide, we saw that probability of A and B could be written in two forms, right? PA given B multiplied by PB, or PB given A multiplied by probability of A. Knowing these two are equal, we can write the Bayes formula in a different way. Probability of A given B equal probability of B given A, so vice versa, how these two are related. So PA given B is PB given A multiplied by PA divided by PB. So basically this formula, Bayes formula or theorem, connects PA given B to PB given A. And the significance of this is that sometimes one or the other one is easier to estimate or calculate directly. So we directly measure or calculate one, and we use the Bayes theorem to find the other one. The example is when we are talking about a diagnosis testing. Let's say the probability of D plus given T plus is probability of having a condition given the test for that condition is positive is equal to probability of the test being positive given the patient has actually have the condition multiplied by probability of having the condition divided by probability of the test being positive, right? So PD plus given T plus is probability of actual positive condition given the test result is positive. PD plus is the probability of someone has the condition. Probability of test being positive is shown by PT plus. But we know that probability of T being positive, test being positive, there are two scenarios. It can be a true positive, it can be a false positive, right? So that's how we rewrite the Bayes theorem or formula for this form, right? So PD plus given T plus, the condition exists, probability of the condition exists given that the past test is positive is equal to probability of the test is positive for actually the condition exists multiplied by probability of the condition exists divided by, and in the denominator instead of P of test being positive we write this, which should be familiar, right? Probability of patient actually have the condition multiplied by a test true positive scenario. T plus given D plus means that the test is positive and the condition is actually exist, plus probability of the condition doesn't exist but we have a false positive, right? So that's how we can get a positive test, either through a true positive on a patient that actually has the condition, or on a patient that doesn't have actually the condition but a false positive is happening, right? So if we replace these P, probability of test positive D positive, with TPR, which is test true positive ratio multiplied by probability of the condition exists, right? So this is what's happening. Probability of test being positive given the condition actually exists. This is a true positive, right? Or we call it true positive rate. In the denominator, we do the same thing and we write it PD positive, true positive rate plus probability of not having the condition multiplied by false positive rate. Now, if you look at this fraction here, you see this term up here is being repeated in the bottom. So to make it look simpler, we divide numerator and denominator by this term. So this is what we get, 1 over 1. So these terms become 1. And then we have P here. We're dividing with this, right? So at the bottom we have 1 plus P, probability of not having the condition, over probability of having the condition multiplied by false positive rate divided by true positive rate. Okay, now let's rewrite this. We know that if we have a fraction like this, a over b equal x over y, that can be rewritten as a over b minus a equal x over x minus y. We do the same thing to this, to both sides of this equation. On the left, we have probability of actual condition exists given the test is positive. This is on the left side. This is on the right side, and we apply this formula, right? And this is what we get. Probability of the condition exists given the test is positive divided by 1 minus probability of the condition exists given the test is positive is equal to probability of the condition exists over the probability of the condition doesn't exist multiplied by true positive rate divided by false positive rate. So in the denominator here, what we really have, what is the complement of this probability? Probability of condition exists given test is positive. Okay, the complement of this probability is the condition doesn't exist, right? So when the test is positive, either the condition exists or doesn't. So these two probabilities are the complement of each other, meaning that 1 minus 1, one of them gives you the other one, right? So that's how we arrive at this equation. Probability of the condition exists after test over the probability of the condition doesn't exist after test is equal to the probability of the condition exists before test over probability of the condition doesn't exist before test multiplied by true positive ratio over false positive ratio, which kind of makes sense, right? Before any test, the ratio of having the condition is this, right? Ratio of having it to not having it, right? If we multiply that by the true positive ratio over the false positive ratio, right? It gives us the post-testing same ratio post-testing, right? That's how the pre-testing ratio of having the condition over not having the condition relates to the same ratio after the test, having it over not having it. Okay, if we want to write it down to make it easier to memorize, it's positive to negative ratio after test is equal to positive to negative ratio before test multiplied by positive likelihood ratio. This is a term that is actually TPR over FPR. True positive ratio divided by false positive ratio is called positive likelihood ratio. Okay, positive likelihood ratio is true positive over false positive. Now, an example. Okay, in this example, we know that the population of the patients have 10% chance of having a condition, right? 10%. And test returns positive with a positive likelihood of 16. What is the post-test probability of the condition? Okay, so 16 is positive likelihood ratio, or is test positive rate divided by false positive rate. If we plug this in the formula, right, from the previous page, this is what we get, right? After test ratio is equal to before test ratio multiplied by positive likelihood ratio, right? So probability of the condition exists given the test is positive over probability of the condition doesn't exist given the test is positive is equal to probability of the condition exists over the probability of condition doesn't exist multiplied by positive likelihood ratio. Okay, so this is what's being asked in the question. Post-test probability of the condition. This is what we need to find. So if we call this x, right, the denominator is 1 minus x. Why? Because these two are complement of each other, right? X over 1 minus x is equal to probability of the condition exists. It's given in the problem. 0.1. What is the probability of condition doesn't exist? It's the complement of the numerator, sorry, is the complement of numerator. So 0.9 is the complement of this. 0.9 is the probability of the condition doesn't exist, multiplied by likelihood ratio, positive likelihood ratio, 16. If we solve this equation here, we get x equal 0.64.